So we're going to build off of the previous video discussing differentiability for a piecewise defined function. This is example 4, which is beneath the notes that you've already taken for our 4 basic rules for differentiation. What we're looking at here is we have another piecewise defined function, okay, but it has lots of letters involved, all right? The main letter, our variable is x, all right? Our function is h in terms of x. So we have ax cubed plus 2x, x is the variable. A is just some constant, it's a number. We don't know what it is, but we're trying to find it. Same thing with k in the bottom part of our function, 8x plus k. K is some constant, we're trying to figure out what it is. In order for us to be able to figure out what it is, we are told that h needs to be both continuous and differentiable. Okay? So building off of the last video, we know that if the two functions, the two parts of the function, are equal to each other at the spot, at the value of x where they change over, then the function will be continuous. And if the derivatives of these two functions are equal to each other at the value of x where we swap from one to the other, then the function will be differentiable. So ultimately what we're looking to do here, two tasks. One, set these two functions equal to each other and let x equal 1 and come up with an expression that connects a and k. And then we're going to do the exact same thing with the derivatives of these two functions, and that should allow us to have enough information to figure out what a and k are going to be. So let's go ahead and do that. So again, in order for the function to be continuous, we know that the top part and the bottom part must be equal to each other when we make the changeover. And we make the changeover at x equals 1. So we're going to have ax cubed plus 2x equals 8x plus k. We're setting the two parts of our piecewise defined function equal to each other. And we know that this is true, we want this to be true, when x is 1. So now we can replace x with 1. And if we do so, we have a times 1 cubed plus 2 times 1, and that's equal to 8 times 1 plus k. Okay, if we simplify this a little bit, we don't nearly need the 1 cubed, nor the 1 here, we just have a plus 2. And over here on this side, we have 8 plus k. So a plus 2 equals 8 plus k. Okay, so we have this relationship, we have this equation, it's got two variables, a and k. So it's similar to something we did a long time ago in algebra. We can't solve this, figure out what a and k are, we don't have enough information because we have two variables and only one equation. We need another equation, and that's where the second part comes into play, differentiability. In order for this function to be differentiable at x equals 1, we need to be able to plug 1 into both parts of the derivative and get the same value. So let's find our derivative. Okay, so we need our f, just separate this a little bit. F prime of x. We're going to use our rules to get the derivative. We have ax cubed. A is a coefficient, so it's going to move right into our derivative. And then we have the derivative of x cubed. X cubed is 3x squared. We've derived that a bunch of times now. So I'm going to put the 3 in front of the a just to make it look a little nicer. So we have 3ax squared. That's the derivative of ax cubed. Because remember, a is just some number that we're trying to figure out. Then we take the derivative of 2x. The derivative of 2x will just be 2. So we have 3ax squared plus 2 when x is less than or equal to 1. That's the first half of our derivative. Now we take the derivative of the second half. 8x. The derivative of 8x is just 8. K is a constant. It's a number. We're trying to figure out what that number is. Constants always derive to 0. So k derives to 0, which means we don't even need it there. Okay? And that's valid for when x is greater than 1. So now we're going to do the same thing that we did over here. We're going to set these two pieces of the derivative equal to each other, and we want x to be equal to 1. So we have 3ax squared plus 2 is equal to 8. And we know that we're interested in this being true when x is 1. So we plug 1 in for our value of x. We have 3a 1 squared plus 2 is equal to 8. And we know that 1 squared is 1. So we really have 3a right here. 3a plus 2 is equal to 8. You've been solving equations like this forever. All right, we subtract 2 from both sides. We divide by 3. And we see that a is equal to 2. Okay, that's nothing new here. You've been doing algebra forever. If a is equal to 2, now we can go back to this equation and we can sub in 2 for a. 2 plus 2 is equal to 8 plus k. Right? 2 plus 2 is 4. So 4 is equal to 8 plus what number? Well, 4 is equal to 8 minus 4, so that means that k is equal to negative 4. So if k is negative 4 and a is 2, then h will be both continuous and differentiable, because when we plug those values in and then we punch in 1, we'll get the same value. And if we plug the 2 in for a right here and we plug in 1 for x, we'll get the same value for the top and the bottom. This is the type of question that they like to ask on the AP exam, hence the reason why you see this as one of our examples, and also on the differentiability homework assignment. So you can go back now to the differentiability assignment and you can tackle that problem.